So gradient descent is great, but there is an issue that happens sometimes. Like, let's just consider the j that you get from linear regression. So this is the average loss, where the loss is defined by wtx minus yn. Okay, and so often people put a 2 here to cancel this 2. Um, okay, so and now if we take the gradient of this thing, you guys are like, oh god, didn't we spend 30 minutes doing this last time? But we're going to do a simplified version now because we're not trying to vectorize it, we're just doing basic calculus. So it looks like this minus yn times xn. So now this is a vector quantity because of that guy, and if you should go over that slowly if you... Yeah, I mean, to be honest with you, these things kind of blow my mind sometimes too. Remember, the gradient is a vector, so this is a vector quantity because this is actually a sum of vectors with all of these things being contributed each time through the sum. And as we do this, we're going over the entire data set. So what if the data set is large? N might be something like, could easily be 10,000, and then in some extreme cases it will be hundreds of thousands. And so this can, now if you do gradient descent for 10,000 iterations, which is pretty 1,000 iterations, which is pretty typical, then for each of those 1,000 iterations you've got to call the gradient function, and then the gradient function has to look through all 10,000 data points to compute this average, and it can take a long time. So there's this really clever idea called stochastic gradient descent. So the way most of these, well, for logistic regression and linear regression, we can think of these error functions as the average loss. So for example, and the linear regression problem that we were just looking at, the error function is the average of this function little e w yn over the entire data set, where in this case, in linear regression, the loss function is equal to 1/2. I'm sneaking in my 1/2 here. Wt xn minus yn squared. Okay, so we're just taking sort of the average loss. And then if I compute the gradient of the error function, then what I get is the average of the gradients of this little e character, which depends on xn w. And we can actually figure out what this is in this particular problem. In this particular problem, the gradient of the loss is just the derivative of this, and so that is Wt xn minus yn times xn, and it's a vector quantity because it's the gradient. So okay, so one way to think of what the gradient is doing is it's averaging the gradient of these little loss functions that just tell you the penalty that you pay for a particular example. So here's how stochastic gradient descent works. But before we do that, let's review let's review regular gradient descent. The way regular gradient descent works is you iteratively do something like, and let's just do the simplest thing that we possibly can. So for 1,000 times, we do w is equal to w minus eta times the gradient of j w. Okay. So this is basically how regular gradient descent works. This is regular gradient descent. All right, and now every time we call the gradient, we have to look at all the data. Okay, so instead of doing that, stochastic gradient descent does the following thing. Let me push this down. There's regular gradient descent. For stochastic, stochastic is a different word for random. It's just a fancy word for random. So you do this for some number of times, but now you can afford to do it more times. So now maybe this is for 10,000 times. You let x be equals a random row of x. So you're picking this row out uniformly at random from the rows of x, and then you're doing this update. Now w is updated to be w minus eta times, but now we're not doing the whole gradient, we're just doing the gradient of e on this particular x, and you need the corresponding y also. So this this y here is just the y that corresponds to x. So x, y is something in the training data, and so that's it. So now let's compare these two. When we did regular gradient descent, every time we looked at the gradient, we had to look at every single data point. So the time that took was multiplied by capital N. But now we're just doing it once, and so that's good. To work less hard, to work 1/10,000th as hard as you were working before is good. So the question, you might ask the question, does it work? Like, why does just picking one of these at random and then updating based on that work? And it turns out to work pretty well, and the reason has to do with expected value. So what's random here is you're picking x sort of at random, uniformly at random, in x. So this is a randomly selected row of x. So you can ask, what is the expected value, which will be a vector, of gradient e? And so this doesn't depend on whether it's this expression or some other expression. This is just totally general. You're picking rows uniformly at random from x. So the expected value of you're picking x at random here, I guess x, y at random. So the expected value of gradient e of x and w and y is equal to the average of gradient e over all the data. That's just by the definition of the expected value for uniform distribution. So now you've got xn wy. So that's the expected value of this gradient thing. But holy smokes, look at this. What is this? That is gradient j. So Yeah, and you can see that actually right here. Okay. So the expected value of just doing it for a randomly chosen data element turns out to be the what we would normally just use, which is the gradient of j. So that means that on average, this process will sort of kick us in the right direction. And it might not work. So I just want to look at this picture. We have a nice plot of a nice contour plot here. So before, when we did this, you saw the points. They sort of follow, like, you know, the best path. That's with regular gradient descent. Now with stochastic gradient descent, they only do the right thing on average. It's like Spike Lee should make a sequel. So it might go there, and then here, and it might even go backwards a little bit. It might need to run for a lot longer, but it's sort of like behaving like this, and then eventually it'll be like that. So that's sort of what stochastic gradient descent is, and it might take more steps to converge, but each step is much cheaper than the step that you were doing when you were doing full-blown gradient descent. So that is how stochastic gradient descent works. And in the next video, I will talk about scaling.